People will still be logging in. That's great. Looks like we have 39 participants. That's great. So I just want to welcome everybody. This is our Advanced Technology and Analytics Seminar Series, and we're not interrupting it. It's coming on as originally scheduled by Zoom, and I think everybody knows this is hosted by myself, Dean Edwards, and the ATC cores, and we'll hear from Joel Sederstrom today. But before we get to that, just a few little instructions about doing this as a Zoom presentation today. I think everybody who's entering is automatically on mute, and we're going to ask the audience to stay on mute for the whole time. We'll open it up for questions at the end, and you can simply unmute yourself if you have a question. But as we go along, and I also ask participants, we'll all turn our videos off and mute ourselves, except for Joel, be the only one talking. There's a chat box. I think most of you are used to that now. If you have questions, you can go ahead and, as we go along in the seminar, put your questions on chat box, and we'll kind of go to those questions in order at the end. And again, you can unmute yourself for the question. If there's any technical issues, you can't hear us or can't see something, put something on chat box if there's any problems. And this is being recorded today and will be put on our ATC website later if people can't see this. And I think Zara Villani set this up, and I think she's setting it up to block people coming in, I think at 10 minutes after we get started, so we don't have any technical issues. But so having said all that, we're just going to get started. I want to introduce our speaker today. I think everybody knows Joel Sederstrom is the director of the Cytometry and Cell Sorting Core, is going to talk today. And Joel actually got his undergraduate and his graduate degree both at the University of Minnesota. And he stayed on in Minnesota, is actually directing the flow cytometry core for the Cancer Center at the University of Minnesota. He came to Baylor in 2006. We didn't really have a good functional institutional flow cytometry core at the time. He was recruited nationally to come and build a core, and he's done a fantastic job, as everybody knows, over the year building up the core. And he's going to be talking today about some of the newest latest innovations and technologies in the core that many people may not be aware of. So we're looking forward to that. So the title of his talk today is Mass Cytometry, Image Cytometry, and Immunophenotyping. So with that, Joel, I'm gonna mute myself and block myself off and leave it to you.
All right, thanks, Dean. I appreciate it. I'm gonna turn my video off so I can make sure to go through without interruptions. But remember, please remember you can ask any questions in the chat, and we'll follow that up at the end as well. All right. So thank you all for coming out. Like Dean said, my name is Joel Sederstrom. I'm the director of the Core Flow Cytometry Core, or the Cytometry and Cell Sorting Core here at BCM, and I also I'd like to point out to my academic director as well, Dr. Christine Beaton, who helps out quite a bit. Matter of fact, a lot of this couldn't be done without her, with her amazing grant writing skills. And if I can get my darn slide, please remember to use Zoom chat for some of the questions during the talk. So a lot of people know about the Cytometry and Self-Sorting Core. We have a lot of different services. Many of you have used us. We do anything from training, consultations, data analysis, cell sorting, cell analysis. Recently, we've had some pretty large changes, and so I wanted to highlight some of these with a talk. Recently, we got a shared instrumentation grant for a large particle cell sorter. We also got a prestigious Core Facility Support Award from CPRIT that allowed us to purchase other equipment as well, including a Helios mass cytometer, Hyperion imaging mass cytometer, a Symphony 30-color analyzer, and then also establishing a mass cytometry antibody bank, which is really going to help out. And I'm going to talk about that. Just to summarize what I'll talk about today, I'm going to talk a little bit about our large particle cell sorter, just a quick blurb so you guys can know a little bit about it. We're then going to talk about the imaging cytometry. Then we're going to go into data analysis as a segue into our analysis services, as a segue into our high parameter analysis services as well. Let's start. I'm going to start with large particle sorting. So we recently obtained a shared instrumentation grant for a Union Biometrica bias sorter. And really what this allows us to do is handle large particles, meaning large cells, up to organisms, entire organisms. You can sort entire C. elegans on this, and small in the actual smaller part of the larvas of the melanogaster. Another interesting part of this particular instrument to highlight is the fact that it's actually very sensitive. It's a lot more sensitive. There's not the pressure differentials of a typical sorter. So you're really going to be able to run out. So people sorting adipocytes, which can vary in size as well as sensitivity, hepatocytes, which also size and sensitivity, as well as cardiomyocytes, which are really hard to sort using a traditional cell sorter due to their sensitivity to the shear forces. There's just a couple highlights on here. You can always come talk to us on this. This does have a little bit of an imaging portion where it actually takes a signal over the entire length of either the cell or organism. So it's interesting. It can kind of determine some heads from tails and the like. We have some interest also in organoids because this can sort smaller organoids. But if you're ever interested in this, please come talk to us. Dr. Bethany Tyner is my lead on this, and we can get you contact information. A little bit, a good portion of my talk is dedicated to imaging cytometry. We have an imaging flow cytometer. It's called the Amnis ImageStream X Mark II. A long title, but it's actually a series of significant improvements to the initial imaging cytometer. Imaging cytometry is really interesting in the fact that it allows you to kind of bridge two worlds. You have the world of flow cytometry and the world of microscopy. And here is an instrument that does both. It's a great capstone instrument. Really what it does is it allows quantification of morphological and spatial features. This is a high throughput data acquisition, somewhere between 300 and 1,000 events per second. And this allows you to have a very high statistical power, which I'm going to touch on. And like I said, it's an easily adaptable technique. If you have an assays already running on imaging or on flow, this can pretty much handle it. There's a lot of different applications out there that are being utilized this, and we're actually seeing more and more every year. I'm going to touch on some real basic ones. I'm going to touch on some shape change, just to describe some of how you can map these morphological features. We're going to talk some about intracellular localization, cell-to-cell interaction, and then parasitology, which is really cool. So here's what the image stream looks like. If you've been through the core, you've seen it in the corner. It kind of doesn't jump out at you. What it does is pretty amazing. In the lower left-hand side, you're going to see kind of an example of the screen of the instrument, where you actually see cells running through and a combination of images. So for every cell that goes through, it takes a stack of imagings, everything from bright field, dark field, to fluorescent images. And then it gives out various plots, just like a flow cytometer would. Now this, just like many of our flow cytometers, this has four of the standard laser: violet, blue, yellow, green, red. It allows you to do most of the common fluors that you're used to. One of the differences where we take into microscopy is that we're using a CCD system and we have multiple objectives. This means that we're using a CCD camera to pick up the images, and we're doing this over time to increase the sensitivity and the reads. So here we'll see you have a 60, a 40, and a 20x objective. Really, this is determined by your cells and what you're doing. A lot of the times, if you're doing cell lines, the 20x objective is fine. Where if you're doing primary tissues, you may end up having to do the 60, especially if you're doing an internalization assay. Now, during the acquisition, we're basically reading one cell at a time, just like a typical flow cytometer. But because we're doing it so fast, we get these image stacks. There's a basically a prism technology that breaks the signal up. So you'll see up here, I have a highlighted cell. This is one cell. We have a FITC channel, a PE channel, a PER-CP channel, or a PE-Cy5 channel, excuse me. We have our dark field, our DAPI, and some others. And really the point here is that we're actually taking this many images for every cell that goes through. And then we can go and look at it in a typical way we would for flow cytometry data. The axes are going to be a little bit different than your normal forward and side scatter, but they correlate very well. In this first particular case, we're looking at single cells using the area of the cell versus an aspect ratio. Then I have a plot here that's looking at that this is just kind of going on dark field for nucleated cells. And here's a gate that we're gating out dead cells as well as CD3 cells. And this is just an example. But obviously, as with flow cytometry, anything you do can be done in multiple ways. I just want to kind of bring some of the highlights to this, especially in the power of this system. For every one of these dots we see is an image, a stack of images actually. So you can click during the process, I can't show you here, but you can click on any one dot and see the image of that cell. In this particular plot here, I've got a CD14, CD16 plot where we have two different populations, one granulocytes, one neutrophils, or monocytes, sorry. And so if we highlight our CD14 positive cells, we can actually pull up a virtual sort. And this is just a small amount of all the images that are in there. Say we wanted to do the same thing for our neutrophils. We could do the same thing. And here you'll see that some of them, that they're expressing various markers. Then you can see the colors. You see a stack of images. And this is a great way to not only see your cells, but you can visually confirm your shape, your size, all that. And now, typically, this is where you go in flow cytometry. We kind of take it on faith that we see that these dots are cells, but here we can see them. And this allows us to do something else. We can start looking at other events in the area. Did we set our gate right? What are these other mystery populations? So I'm gonna take one example or two examples here. Here's two populations that are two small populations in between our 14s and 16s. This first green population, which is dim for CD14 and dim for 16, you actually notice that the cells are expressing both. The channel on your right is actually a combined channel between the two of 14 and 16, and you can see that it's one cell expressing both. This could be, this is its own real population. But if we look at the orange population, what we're seeing that these are all doublets. Yes, we put a doublet discriminator on, but apparently it wasn't quite as good. And so we can verify that here just by imaging. So now, what another thing we can do really readily here is shape. So just to kind of bring on how we bring these features into analysis. Here is some PBMC that's been, or monocytes that have been incubated with the chemoattractant, and this causes them to change shape and mobilize. They've also been labeled with CD14 FITC so it lights them up. So if you analyze these, what you're gonna see is a bright field image, a dark field image, and a fluorescent image, and you can combine these up. But really where the power is we can then start adding statistics to it. So what we're gonna do is we're actually gonna do a radial measurement, right? So we're just gonna measure the radius from the center of mass out everywhere. And so we have two cells here. We have untreated and treated, and you'll see that there's no radial variance in the untreated because it hasn't gone through the shape change. But the treated have actually gone through this. There's a radial variance. This radial variance can actually be divided, can be averaged and divided to create a feature called circularity. And this circularity gives you a number. So on the left, on the histogram on the upper left is unstimulated cells, and the upper right is stimulated. Now you'll notice that the unstimulated cells have kind of almost a Gaussian distribution. And if you look at either side of these actual circularity numerics, you will see on the right side is more circular, the further you get to the right, the more circular it is. And the further you get to the left, the least circular it is. Now, if you notice the histogram on the right, you see after it's been stimulated, you see a shift to the left or a loss of circularity. And that's shown in this virtual sort images below. And whenever you see images like this, you're only seeing a small caption of it. Remember, we recorded probably somewhere between 5,000 and 10,000 events here. So these images represent somewhere like 2,000, 3,000 cells easily. You can do this for a lot of other morphological features. One of our favorite assays is translocation, specifically NF-kappa B. NF-kappa B, to do it via flow cytometry before, you'd actually have to label both NF-kappa B and phospho NF-kappa B, and hope that your phospho NF-kappa B labeling is done well. Otherwise, you're going to have a lot of background, and it's going to be problematic, and you'll never be able to verify. With this system, you can verify it and see it immediately and only have to label for NF-kappa B. In this particular case, is labeled with a nuclear probe, which is DRAC5, and then NF-kappa B itself. So if we use this, we can actually use something called a similarity, or what we're basically meaning an overlay. It goes pixel by pixel, and if it compares one fluorescence to the other. And so if the more similar it is, the further it goes to the right. The least similar, the further it goes to the left. And in this particular case, that's indicative of nuclear translocation because of our DNA probe. So you'll notice untreated cells on the left here are unstimulated, and so their NF-kappa B is in the regular part of the cell. You'll notice after stimulation with LPS for an hour, we get nuclear localization, and you'll see that the combined images give us this bright DRAC5 NF-kappa B co-staining. So this has allowed us to do some fun stuff statistic-wise. So Dr. Mendoza let us use this data, which he was comparing a drug. He wanted to see what this drug effect is on activating monocytes. In this particular case, we have CD14 cells. We've got 3 groups. One of them treated as a control. One with LPS stimulation, which we know is a very robust stimulation method for monocytes, as well as a mystery drug, we'll call it. So what he was able to do is we did the analysis on all of them, on the controls, on the LPS stim, and the PCV stim, and then we'll check for translocation. And if you look at this plot on the lower left side, you see the blue is the control. There's always in this case you'll see a little bit of stimulation. Then you'll see the drug, which is basically right in between our LPS stimulation and our control. Well, now this is a pretty picture, and some people say, oh yeah, that's great, but how do I actually analyze that? Well, you can do some interesting things. Like in this particular case, I took a Fisher's discrimination ratio, and really all I did was took it and compared our 2 drug stims to the baseline control, and this gave us a statistically robust method to compare them. And this is just because we have done so many numbers. In this particular case, it was probably each group was at least 20,000 events. Now, this allows us to do some other things as well. Now, let's go a little bit beyond the cell, cell-cell interaction. Dr. Maria Bettini was interested in seeing the interactions between T cells and antigen-presenting cells. And in her particular case, she was really interested in Tregs. Well, she labeled up cells with anti-CD5, which is a T cell marker, CD4, another T helper cell marker, FOXP3, which is a Treg marker, and then a couple antigen-presenting cell markers, CD11C for dendritic cells and B220 for B cells. She basically co-cultured these, labeled them, and then we did some analysis. On the upper left plot, just like a flow plot, you'll see CD4 versus CD5. CD5 is a pan T cell marker similar to CD3. And so we're selecting all of the cells that are CD4 and CD5 positive. Now, we haven't eliminated doublets at this point. We then go and look at our plot where typically we eliminate doublets here, and we would select the single cells, but we're not. We're actually selecting for doublets here. We actually want to get conjugate pairs. So we select the doublets, and we analyze that with CD11C and B220, because we're going to find the groups that are being stimulated by antigen-presenting cells. We can then take this for further analysis. On the left, you're going to see CD11C DC conjugates that are conjugated to our T cells. And these are differentiating between our Tregs, which are expressing FOXP3, and then our CD4 helper cells in general. And you can see the same thing with the B cells. Now remember, this technology allows you to do the virtual sort, so you can actually look at all these images. I've got a representation of just 4 or 5 images each, but all these are just stacks of images. So you can see if you look on the Treg, so I've got a row of Tregs and a row of T helpers, and then they go underneath our CD11C and our B cells. An example here, you can see this little purple staining in our top. See all these cells have a little purple stain? That's not DAPI or DRAC5. That's actually our FOXP3. FOXP3 is locally located in the nucleus. So we can visually verify that these are actually Treg cells, and you can actually see them conjugated to their corresponding antigen-presenting cell. And then this allows us to do analysis as well. So I'm going to move on a little bit to even more interesting other interesting applications. Our National School for Tropical Medicine came down to BCM, and we've been really excited working with them. There's some neglected tropical diseases that they're working on. And one of them is Chagas disease. Chagas disease is caused by a T. cruzi parasite that gets in your blood from what's called a kissing bug. And I'm not going to go through the cycle of that. If you ever get a chance, Leroy Verstig gave us what allowed me to use some of his slides. He does a great talk on this. We had him at Flotex, and it's really a great story unfolding. So in this particular case, we're actually looking at T. cruzi. T. cruzi, in the part of their life cycle in the human, they have 2 forms. They have amastogotes and trypomastogotes. You can see down here, the amastogotes are generally small, round-like, non-mobile cells that will be either pulled into a cell or they're the form inside of the cell. And then you've got these trypomastogotes, and these are little wiggly things that'll actually, they go through, and they're the ones that actually go seeking the cell and then escape from the cell. Now we're able, because of their differences in morphology, just like our doublets and other things, we're actually able to tell the difference just on the bright field versus aspect ratio plot. We can see the amastogotes versus the trypomastogotes. Now this is interesting. Now here's just verification. We're validating this is an antibody against our T. cruzi, and this is a vital dye that the T. cruzi are labeled with. And this is all nice. It's very nice to see these images, but how does that really affect Leroy's research? Well, they're looking for vaccination strategies to perhaps help the third world countries that have issues with this. So they want to start analyzing this in human cells. So here's an example of amastogotes that have been incubated with macrophages. And now what you see is the labeling of our T. cruzi, and you also see the cells themselves. Some of them are on the outside, some of them are on the inside. And this allows us to start doing some interesting assays and get some interesting statistics. So the imaging cytometer has a masking capability, basically just a way to analyze images. And here's an example of our T. cruzi in macrophages. We can create a mask. In this particular case, it's an internalization of road mask. Really what it's doing is it's doing that center of mass of the image and kind of bringing it back, dialing it back. And it's giving an analysis. So the higher it is in score, the more closer to the center of mass it is. In this particular case, that means internalized. So now we can tell the difference between non-internalized T. cruzi and internalized T. cruzi. This would allow you to do various things to kind of tweak and create your vaccination strategy. So in this particular case, I'll just quickly go over this. They used serum from infected mice. They showed that the serum from infected mice actually decreased the amount of internalized amastigotes in myoblasts and increased them in mouse macrophages. And that might even be indicative of an immune response and what's supposed to happen. So this is just another way to bring images into a statistical analysis and bring a powerful tool to use. Now, obviously, that being aside, we've got other things than our imaging cytometer in the core, all of which are great options. We've been doing into the core and for a while, ever since we collaborated on a grant with Monica Justice a long time ago. That was an international mouse phenotyping consortium. And we've had a mouse phenotyping panel from them. And it's carried along in the core. We've done it. We've helped some people. It's a basic panel. We have a one panel that's for T, NKT, and NK cells. We have another panel that's for B cells and myeloids. This is in spleen. This were designed originally in spleen. We've actually added CD45 to this so that we could then take it to other tissues. And since then, we've done everything from ovarian cancer to infarct versus non-infarct hearts, just to mention a couple. And this is kind of one of the things that brings me into our kind of advanced phenotyping as well. So I'm going to start off here. Let's first talk about the workflow of a typical immunophenotyping. So we take it, we disassociate our tissue, and we label it with our panel. We're going to run it on a cytometer, and we're going to analyze it. Now, typically, we analyze it with a template that we've already created in the core. But you know, all those templates are created from an aspect of immunological standpoint, and so it's not as discovery as much. So what we do is we've added a feature, which is we're taking a cue from our larger scale assays and adding a dimensionality reduction and clustering algorithms. So first, what we do when we're analyzing our data, we're going to do some data pre-processing. This is through Flow AI and FlowJo. So this is going to remove errors, some doublets and all that. If you look at these first two plots, this is actually Flow AI cleaning up the data. In this particular case, this was probably a clog. And what it's doing is it's looking at this data over time on one of the lasers that are furthest away from the timing laser. And you can see that this is now creating a gate of good events. And then from now on, we're only going to analyze good events. Then we're also going to look and do some of our normal things. We're going to discriminate against doublets. We're going to also select our viable 45 positive immune component. And this will allow us to do a more succinct analysis. So the next step in this analysis is dimension reduction. So this dimension reduction, basically what we do is we take the data, we create it we make sure that they're all starting with all the same numbers so we don't skew it versus one way versus the other. And this would be multiple files, mind you. And we create this dimensionally reduced plot. Now, many of you guys have seen the Tisney plots, and they're getting kind of popular, but there's just kind of a little background on it. All right, so from the Tisney, and we do the Tisney first. From the Tisney plot of the dimension reduction, we then go to a clustering algorithm. In this particular, we're either using Phenograph or FlowSum. You'll notice that now our Tisney plots actually start having clusters associated with them. These clusters all kind of correspond to various types of cells, which we'll see in just a minute here. Now we have to do something with this cluster. So we're going to do clustering analysis, and this is kind of a simplified version here. This particular case is data from Dr. O'Malley's group. They were doing a knockout mouse versus a normal mouse, and we're just analyzing spleens. In this particular case, you'll notice that we come up, if we're looking at FlowSum clusters, for differences between the clusters is where we're ranking them, where the first two with the biggest differences correspond to two populations, populations 1 and populations 2. So let's take this data just a step further here. So here is our t-SNE plot with our populations 1 and 2. Here they're highlighted in between the wild type and the knockout mouse. And here you can actually do a little bit of a quick phenotypic analysis to figure out what those populations are. You'll notice that in the wild type mouse, it's lacking this group here, and there's a large group over here. And this is just a wonderful discovery tool, because we're like, okay, well, what's going on there? So then we'll look over it at our phenotype and try to figure out what those are. Well, it turns out that group 1 is actually CD11C high, which is typical of dendritic cells or antigen presenting cells, where our group 2 is B cells or B220 high. So what we're finding here is that in wild type, there's fewer dendritic cells and a lot more B cells. Well, here in the knockout, there's a loss of B cells. If I remember correctly, this particular knockout model affected the Tregs, and so this is why you're seeing some of these immune subcomponent differences. So this brings me to high parameter cytometry. This is the method this is the discovery methodology that's been brought up in high parameter, because you're just dealing with so much data. But it doesn't necessarily have to be used just in the super high parameter space. So a little bit about our high parameter unit. I've been talking about this. If you can't get me to shut up about it sometimes. Christine got us this grant from Secret, and it's been phenomenal. This allowed us to go into Mass Cytometry. In this particular case, we purchased a Helios. The Helios is the 3rd generation Cytoph. Basically, what it does is it allows you to run isotopically or metal tagged human and mouse or anti-human and anti-mouse antibodies. And I always call this a fluid analysis pipeline, where it's more similar to flow cytometry. Really, and I'll show that in a second. Then we also have the Hyperion. The Hyperion is an addition to the Helios, which is an imaging portion. It is a laser ablation unit that will take slides and ablate the slides at 1 micron at a time. And this works on both frozen and formalin-fixed paraffin-embedded tissues. It does have a tendency to use different antibodies, at least for the FFPE samples, due to the antigen retrieval process. And in this case, it's an image analysis pipeline where it adds a couple steps in it. Now, additionally, our high parameter unit also is creating what's called a mass tagged antibody bank. What we're doing is we're purchasing commercially available pre-tagged antibodies in bulk, and then we'll be setting up panels for people. We're also going to be, we're also purchasing antibodies in bulk and conjugating them ourselves just to reduce cost. The cost saving actually can be quite dramatic. There was one where it was compared to the commercially available probes. It was just a 100-fold reduction in cost. Additionally, now and we're doing this antibody bank model in conjunction with MD Anderson. They're helping us a ton out they've been doing a human antibody mass bank for quite some time. We really want to just open it up to our investigators and keep that price down. So we also have a Symphony A5, which is a 30-parameter, a 30-color flow cytometer. It is actually set up with 50 PMTs, so at some point this will jump up, whether we end up taking it to spectral cytometry or just add that many more colors. And this will be available soon to trained users, so people who have been trained with the LSRs will be able to just get an additional training to utilize this instrument if they need to. Here's an image of our Hyperion and Helios. We haven't named it yet. We'll come up with a name eventually. So you'll notice on the left is our Hyperion. This is actually just comes on and off the machine. Not a totally easy process, but it can be done, and we have tape on the floor to ensure it goes back to the exact right spot because it's critical. And then on the right, you see our Helios, and that's the actual mass cytometer itself. This runs mass tagged antibodies, and currently there's 44 metal tags available commercially, and I'll get into that. Basically, all it has is an antibody that has around 100 atoms per antibody conjugated to them. There's also DNA intercalators that allow you to label DNA, which is important. Just to take you as a workflow through mass cytometry, first what you do is you label your cells, and every one of these antibodies is going to have a different mass tag on it. This can be both internal and external, so intracellular and extracellular. Then these cells are run through a nebulizer as they're in liquid form. This nebulized cell stream is then through induced coupled plasma torch. That's basically the heat of the sun, and it turns all that's going through there into ions. Now, this is a large bit of ions, and we don't care about all the ions. Matter of fact, we care about only the mass tagged ions, which are larger than 70 in atomic mass. So what it goes through then is a quadrupole. This quadrupole just removes our light, overly abundant ions, perhaps carbon and oxygen and the like. Then only our heavier metals go through. And then this goes into our time of flight chamber. And this is where our detector is. And this detects each individual mass. From this, we discriminate for cells, and every cell will have, just like in flow cytometry, a signal associated with it. And this creates an FCS file. And then these FCS files can be analyzed just like you would flow cytometry. Now, the panel design obviously is a little bit more intensive. When you're talking about, in this particular case on the right, I've got 30 markers set up there. This is the Fluidigm Immune Profiling Kit. Basically, it's a kit they've already pre-set up with 30 markers to do a complete immune profiling in humans. This can be quite complicated. Right now, we've got 44 metal tags available commercially. There are 58 total metal tags published, and we're looking into that. Theoretically, we have the possibility of 135 channels. Some of these channels are used for cell ID, meaning a DNA label, viability, or DNA proliferation. There is also available barcoding. The barcoding is just helping in multiplexing. And what it does is it really helps in minimizing sample-to-sample variation. This particular example, like I said, is a combination of the viability channel cell ID, which is DNA, and 30 markers that's available from Fluidigm. We have purchased these in bulk as well, and we'll be helping people to utilize these. But we're making our own as well. So here's an example of a design tool. So when we're putting a panel together for someone, and obviously we're in our infancy on this, we've only been doing this for the last 4 or 5 months. But what we do is we take our known masses, and we take the abundance of our targets, and we use this design tool by Fluidigm. And what we can do is, if you look at our heat map here, green is good, orange is not so good. That means that there's spillover. Now, this isn't fluorescent spillover like you'd think of in flow cytometry. This is mass spillover, right? We have various things. If the metals get oxygenated or basically oxidized, that adds 16 mass units onto it, and that can be if a certain percentage is there, or perhaps it's not perfectly isotopically pure. Perhaps there's a little bit of impurities, and that's what causes this. So what we can do is you can move around some of this when you're doing your panel design, and you try to get as less orange as possible. So, and the left would be a not so good example, and the right is a better panel setup. So to walk you through the process a touch here, what we're going to do is we're going to fix, perm, and label our cells. This is one of the potential, at the fix and perm stage is where you would do your barcoding if you're going to barcode, and then you would label. You would then run on the site on the Helios. Then afterwards, individualize and normalize the data, which includes deconvoluting if you're doing a barcode. So then you're going to analyze it. Now, depending on what panel you're using is how you're going to kind of set up analysis. And I'm going to kind of walk you through just a quick little kind of more advanced analysis like we did with immunophenotyping. So here's just but before we do that, here's an example of mass data. I'm sure a lot of you have seen this. This is some of the data that was published back in 2011 in Science. You look on the left, we have conventional flow cytometry. We have an immune panel. This is potentially breaking out, looks like lymphoid, basically B cells, T cells, NK cells. If we're looking and we look at our cell percentages on our conventional flow cytometry versus mass cytometry, they're very similar. Matter of fact, they look very similar. Now, there are some differences. Obviously, especially when you get close to zero, we don't have the mass cytometer doesn't have the noise that a flow cytometer has. There's not light to interfere with it. It doesn't have as much noise, I should say. So you can actually get zero mass readings. So this is why the data is going to look a little bit. Now, I will say that the software kind of makes up for that, and you can offset it slightly to make it look a little bit more like flow cytometry data. Now, you can go further, just like we did with our immune profiling. In this particular case, we're going to do some data processing. All right, so we're going to go ahead, and first we're going to go for DNA. This is an iridium label for the DNA, and we're going to select only DNA labeled events as cells. We're then going to go and do a live dead, where anything that was live at the first point of the live dead fixable assay is going to be selected. The dead cells are excluded. Then we're going to go through after that and do our dimensionality reduction, just like we did prior. This is just a plot showing you 35 different proteins heat mapped into the t-SNE graph. So for each channel we have, you can start seeing where they fall. Obviously, blue is no expression, orange is high expression, and this is kind of the immunophenotyping. So now we can go to our clustering algorithm. Now our clustering algorithm, it starts putting more into it. It starts looking at our clusters, creating populations. This particular case, it's once again FlowSum. Oh, sorry. That's my fault. Sorry, hit the wrong key on my keyboard. I'm not used to doing this Zoom quite yet. All right, so once we've done our clustering, we can then start looking at it, right? So we're gonna do our cluster analysis. In this particular case, what we're doing is we're looking at two different clusters here. We have cluster 0 and cluster 5. So if we look at FlowSum group 0, so here, if you look over, here's our t-SNE plot, right? Here's our group 0, here's our group 5. We're gonna have at group 0, if we're gonna look at the percent viability, let's see here, percent viable singlets here. So we basically have, of the percent viable singlets, sorry, we have different amounts we have differing values between our wild type and our IL-10 knockout. Now, if we switch this and look at group 5, we actually have it inverted, where we actually, our IL-10 knockout is, oh, my mouse just went. Sorry about that, my laser just went. I will just say, this data I just added this morning. Paul sent it over to me, and so I apologize for not having this totally down. Really, right now, the key point takeaway messages here is we have a quick comparison of two different populations through the data, and we're doing this through this cluster algorithms. Here's just an example of that data, right? So this is population 5 selected, and we're looking at what its expression levels are. And this is where you'd actually go through and you could tell what it is. And once again, these are great discovery tools. This is not exactly how you're gonna always look at your data, but you can quickly put this up. You can definitely quickly put this up and know that this is a CD11C positive, PDL1 positive cell. And so you know that it's something along the kin to a dendritic cell. All right, so that was our liquid analysis pipeline. Let's talk a little bit about, in the last remaining minutes I have, let's talk a little bit about our imaging mass cytometry. Now, the imaging mass cytometer is still the mass cytometer. It just has a laser ablation tool added to it. So kind of like a plate reader reads individual wells, this ablation tool does the same thing. It goes to one point, does a micron ablation using a special UV laser, then it goes to the next and the next, and then these ablations go through the mass cytometer. So the workflow on this is a little bit more intensive in the fact that you have to spend a little more time designing and conjugating your probes. There's not, especially in mouse, there's not a lot of probes out there. And these probes have to be validated against antigen retrieved samples, meaning we're talking pathology slides. We're talking paraffin embedded formalin fixed paraffin embedded tissues. Now you can use frozen tissues as well. You're a little bit more under the time then, and you can use a little bit more normal antibodies on frozen tissues. So what we're going to do is design our experiment, conjugate our probes. You're going to do slide prep. We work with the pathology core to do our slide preps, and then we're going to label with your antibodies. You're then going to run on the Helios Hyperion system. This can take, sometimes we're running the instrument overnight. It can take, it does not go very fast. You're typically, I believe it's for a 3 micron by 3 micron area is 17 hours. So you're not going to do the whole slide. What you're going to do is you're going to pick regions of interest. Usually you're going to use a section of H&E staining that's next to your slide, so that you can define these regions of interest. And then after that, what you're going to do is you're going to normalize your data. You're going to segment your data, and then you're going to move on to your analysis. So let's talk a little bit about that. So on your left here, I have a picture of actual data from our Hyperion. This is a kidney section labeled with various labels. On the left is our segmentation. We call it the Fruity Pebbles plot. All the individual colors do not mean anything other than different cells. This is just so we can see where all the cells are. Now, this image on the right is the exact same image, but this image actually has data in it. This is the data from, this has everything in red is SMA, cyan is CD44, our E-cadherin is the lime green one. We have phospho-ERK1 in there, and of course the blue for DNA. And this isn't all the markers in this slide. This is just a representation of it. After about 5 colors, these slides start to get a little blurry. So this slide could technically be all the way up to 25, 30 colors deep, have that many different channels. We're just coloring it as we see. Now, an example here is if you look at the lime green, you can actually see the structure of this kidney, and you can see that that E-cadherin is right around these microvesicles. So you can see that there's structure, and every place you see these dark blues is a cell nucleus. Now you take this, and these two overlay each other. So everywhere where you see a fruity pebble, this will overlay to a corresponding spot on here, and you have all that analysis. So now we've taken all this picture, turned it into individual cells, and are now able to do analysis. Now, the real power of the imaging cytometry is we also add spatial information. We have spatial coordinates. We can see where the relationship between cells. So here we can take this and then go through, after our segmentation, go through our normal analysis. In this particular case, unfortunately, I didn't have data from that one ready to put up. I do have an example here. Here's our Tisney plot, or our dimensionality reducted plot of combined 9 mouse lung tissues. And right here, we're going to query population 7. So here you can see I've got population 7 highlighted here. This is after flow sum. This is our clustering algorithm. So we're now clustering it and figuring out what they are. Now we can then take this, and this is just a quick example for y'all. We can then take this and then say, okay, well, what is population 7? Well, highlighting population 7 here, we can actually see histograms on the right. This potential population is CD45 positive, CD11B positive, CD11C positive. So we're talking some type of macrophage or dendritic cell here. And you can just see wherever there's blue is representative of our population 7 on here. And there's obviously more histograms than that. I showed you earlier in our other data. This is just for the sake of example. This is an example data set that a lab was sharing. Unfortunately, this COVID-19 stuff is we were just starting to ramp up our conjugation and our imaging, and it's kind of put a monkey wrench in that. So a little bit about where we're taking this in the time to wrap up. Future directions. First of all, we're going to continue developing our analysis pipeline for mass imaging and flow. Right now, we're currently working with biostatistics and informatics core. We're working with Dr. Sandy Grimm. She's awesome about this. She's really starting to just dig into this, and we're kind of doing a combined effort so we can have this analysis pipeline for our users. We're going to continue working on the image cytometry. This is both the imaging mass cytometry and the imaging cytometer. We're working with the human tissue acquisition pathology group, core HTAP. They do our sectioning. They're helping us do a bunch of stuff, antigen retrieval and all that. Patty's awesome. And we're then going to also, for our imaging cytometry, which you remembered, they're actually adding new algorithms to their software. So we're going to explore their new artificial intelligence assisted imaging cytometry. When you're creating these images from imaging cytometry, there's so many different parameters that you can add that it really makes sense to utilize the new artificial intelligence algorithms out there. We're excited. Then we're going to continue working on our mass tagged antibody bank. This is also going to include a fluorescent antibody bank because we have to use it for validation. And so we're probably going to end up making that available as well, since we have to keep them on hand. We're going to work with BCM investigators to develop this. Our CPRIT mechanism allows us to issue some pilot grants. Just let us know if you've got a cancer-related project that you want to look into. We're going to continue to work with MD Anderson, especially when it comes to the mouse antibody banking. We're working with some industry members that can help us give us antibody, so we can find, especially in imaging mass cytometry, where there's not a lot of mouse antibodies available. Finally, we're going to investigate spectral cytometry. This is really the new fluorescent cytometry coming down the pipelines. As a matter of fact, some people have already been using them. There's a couple out there in the BCM and TMC, the Texas Medical Center. So we're going to take a look at it. I've been evaluating for a while. We're going to see about getting funds for an instrument, as well as potentially utilizing our BD instrument as a spectral cytometer. We don't know exactly. Matter of fact, I would love if someone out there has a little background in flow and is interested in this. I still have a position open for a flow cytometry technologist 3. I really need a person who wants to really delve into high parameter flow cytometry it would be. So if you know anyone, or if you're interested, go ahead, let me know. And we're gonna, like I said, we have an open position, even during COVID. With that, I'd like to say thank you. Obviously, my flow group, the CCSC group, with my lab manager Amanda, Brandon, obviously Bethany and Leilani and Madhavi. Obviously, we've expanded. We've gone from me having four people to 8 people now. Obviously, lot of this presentation couldn't have been done without Paul Porter, Wago, and Patricia. They're my high parameter group. Obviously, I'm going to thank always Christine for the support, as she's such a key player in the group. Without the grants, we couldn't do it, and she's such a great soundboard for me. As well as I'd like to thank our ATC core administrators. They've been really helpful in this, and we go through a lot. But I appreciate it. Everything from budget, anything they can take off my plate so I can actually start doing science is awesome. Thank you for the data contributors, Leroy, Dr. Mendoza, Maria Bettini. I don't want to massacre his name. Also, thanks to Jared Burks. Dr. Burks has been phenomenal in Mass Cytometry. He's helping us set up. We have a local Mass Cytometry user group, and he's really spearheaded that. But he's just talk about a scientist who just wants to be open and share technique, and it's awesome. Obviously, I want to thank industry, the Millipore Fluidigm, and BD as well. Unfortunately, I didn't put it up there. Sorry about that. And thank you guys for sitting through my talk. I'm going slightly over here for questions. So let's go ahead and open up questions. I will say, we thank you all for voting us as the core of the year of 2019. Here's our picture. We appreciate it. We are trying to do our best to serve y'all and make sure your science is awesome too. Thank you.
Thank you, Joe. I don't know if everybody can hear me, but this is normally where the audience would applaud, but we'll just say thank you very much and open it to questions to Joel. And I think some questions are being answered, if people want to look on the chat box, by Paul Porter has been going through and answering some of the questions, but I'll turn it to Joel. You want to go look at, either ask him a question, or I don't know if you want to go through the chat box first, Joel.
All right, let's see.
And then open it to questions.
Let's go through the chat box real quick, see if there's anything that Paul didn't get to. Yeah, so it looks like Paul got through a couple. If there's anyone who has questions on there, actually, yeah, there's not that, why don't we open it up for verbal questions?
I have a question. This is Jamie Xu. I have a question for you.
Yes.
Beautiful presentation. I'm particularly interested in that tissue slides, and then use different antibodies and identify serotypes, and then you can analyze them. So my question is, so the format you're going to set up is so the core holds all the different sets of antibody, and the users bring their slides, or you want every user to develop this panel?
So we're going to allow panels, and we'll allow people. So it really depends. We'll most likely have you stain your own slides. We'll help you with the antigen retrieval and help stain your slides, and potentially provide you antibodies as well. We haven't got all the details worked out yet. This is one of the reasons we're working with Patty in the HTAP, and we're going to just kind of take it as it goes. We've got one particular active group, Dr. Burt and Dr. Lee's group. Dr. Lee just got a CPRIT high risk, high reward grant that's going to be utilizing it quite a bit. And they do everything themselves. They buy their antibody themselves, they label it themselves, and all they want to do is bring the slides. There's other people who have none of that, and we'll have to do it. So we'll have to do the antigen retrieval and the labeling for them. And obviously pathology is going to do the sectioning and the prep. Mm-hmm. So I don't have a full answer, but we're flexible, and we'll work with you the best we can.
I see. So my opinion, the best thing is the lab can do their staining, but the core might have the antibody panel to share. That would be most economical way to do that.
And it will. And that's one thing we will do.
We do a lot of immune staining with mouse and human tissue cancer sections. Maybe sometime we can discuss about it.
Yeah, of course.
I think there was one question about the recording. I don't know if Zara's on there. I think this seminar will be the recording of it uploaded on the Advanced Technology Core website. I don't know if Zara's there to comment, but it should be uploaded on the website.
Yeah, the seminar is being recorded, and it's still being recorded for questions as well. Once the call is completed, we'll be uploading it shortly onto the ATC seminar webpage.
All right. Well, if there's no more questions, we'll give it a minute more. So nice. We had at least 66 people today. Well, thank you all. I really appreciate the time to give me this time. If you guys have questions, you can always come talk to us. Obviously, in this pandemic, we're doing a lot more meetings via Zoom and email. If you've sent me an email and I haven't got to it, remember to email our group at either at ccsc@bcm.edu for the regular flow core, or you can email us all at cytometry@bcm.edu, and that'll get questions to all of us. And that's usually the best way anyways, because then my people can kind of yell at me and make sure I answer emails, or I can get someone else to answer them. So other than that, if you have, we can set up meetings via Zoom, and we're open. We're trying to figure things out, at least help people during this time. Also, you'll see some emails. If you haven't got them, I'm sure you have, probably too many. I'm sending around some educational opportunities via Zoom, everywhere from we're hosting someone on spectral cytometry this Thursday at 3, as well as we have there's an educational opportunity on Friday, and this is in collaboration with Sloan Kettering. Otherwise, we'll have some more stuff coming up. Some vendors are throwing it. So if there's any particular topic you have an interest in regards to cytometry, let me know. I can probably get someone to set up to do a talk on it in this time of pandemic. All right. Well, thanks all.
Okay,
I think that's it.
Yep.